Feed-forward 3D reconstruction models have fundamentally changed how we approach multi-view geometry. By replacing traditional multi-stage optimization pipelines with end-to-end transformers, models like Depth Anything 3 can infer scene geometry in a single forward pass. But there is a critical gap between academic benchmarks and real-world deployment. These models are trained and evaluated on clean, degradation-free imagery. In practice, captured sequences suffer from motion blur, sensor noise, and dynamic artifacts. When degradation hits, the learned feature representations become less discriminative, cross-view matching breaks down, and the final 3D reconstruction collapses. Feed-forward architectures lack explicit mechanisms to correct these errors, allowing degradation to propagate and accumulate. Improving robustness under imperfect inputs remains one of the most pressing challenges in computer vision. The intuitive fix is a restore-then-reconstruct pipeline. You run degraded images through an existing restoration model, then feed the cleaned outputs into the 3D reconstructor. But this approach has two fundamental flaws. First, most restoration models operate on single views. Processing each image independently ignores complementary multi-view information and cannot enforce cross-view geometric consistency. This leads to view-dependent artifacts that directly poison the downstream geometry estimator. Second, multi-view restoration methods that do exist often rely on heavily compressed VAE latent spaces. While compression improves generative efficiency, it creates an information bottleneck. Fine-grained spatial structures and high-frequency details essential for precise cross-view correspondence are discarded. The result is suboptimal restoration and degraded 3D fidelity. So where should restoration actually happen? The answer lies in the representation space itself. Modern feed-forward 3D reconstructors use multi-view transformer encoders that explicitly learn geometry-aware feature representations through cross-view attention. These intermediate features are already structured for scene geometry estimation. Instead of fighting degradation in pixel space or losing it to compression, we can denoise directly inside this geometry-aware feature space. That is the core idea behind GARD, geometry-aware representation denoising. Let's walk through the architecture. GARD operates on a frozen feed-forward reconstructor. The backbone consists of an L-layer multi-view encoder, followed by a geometry decoder. GARD inserts a diffusion-based denoiser at layer K in the standard setup. K is set to 18 in a 40-layer encoder. Degraded multi-view images are encoded up to layer K, producing intermediate feature representations. These features are passed into the GARD denoiser, which refines them by removing degradation while preserving geometric structure. The restored features then propagate through the remaining encoder layers. From the final refined features, 4 multi-scale feature levels are extracted and fed into 2 decoders: the original geometry decoder for 3D scene reconstruction and an adapted RGB image decoder for high-quality image restoration. The entire process runs in a single forward pass without retraining the underlying backbone. The denoiser itself is built on a die-TDH architecture adapted from representation autoencoders. It uses a wide decoder structure augmented with interleaved attention layers. Frame-level attention captures local spatial structure within each individual view, while global cross-view attention aggregates contextual information across the entire camera array. This design explicitly models multi-view dependencies, allowing the model to enforce geometric consistency during denoising rather than treating views as independent. Training dynamics are where GARD diverges from standard diffusion approaches. Conventional latent diffusion models define flow trajectories from pure Gaussian noise to clean representations. GARD uses interpolated flow matching. The source distribution is a mixture of the degraded latent features and Gaussian noise. This is a deliberate architectural choice. Pure Gaussian noise contains no structural prior, making it difficult for the model to learn meaningful correspondences. By starting from a noise-perturbed degraded state, the denoiser retains partial structural information from the input. This structural prior significantly improves robustness and allows the model to learn a more direct mapping from degraded to clean feature distributions. But flow matching alone does not guarantee geometric alignment across views. To fix this, GARD introduces an attention alignment loss. During training, target correspondence maps are constructed by unprojecting clean multi-view inputs into a shared 3D coordinate system, pooling the resulting point clouds to VI-T patch resolution, and computing pairwise negative L2 distances. A temperature-scaled softmax is applied to generate sharp attention targets. The alignment loss uses cross-entropy to force the denoiser's global attention heads to focus on geometrically corresponding regions rather than spurious blur artifacts. In practice, a temperature of 0.01 is used to maximize spatial localization. This explicit regularization produces sharper attention patterns and ensures the restored features maintain cross-view consistency. The ablation studies reveal why these components must work together. Attention alignment does not consistently improve performance when paired with standard flow matching, because pure noise initialization lacks the structural grounding needed for correspondence learning. However, when combined with interpolated flow matching, it yields consistent gains across pose estimation, 3D reconstruction, and depth accuracy. The degraded input provides the geometric scaffold, and the attention alignment refines the cross-view focusing behavior. Validation on the DA3 benchmark with controlled motion blur degradation confirms the effectiveness of this design. GARD significantly outperforms single-view restorers like Restormer and HIDIF, video-based models like VRT and FMANet, and VAE-based multi-view baselines. Pose estimation AUC30 scores jump substantially, indicating more stable camera trajectory prediction. 3D reconstruction F-scores improve across indoor and outdoor datasets, with depth maps retaining sharp boundaries and fewer spatial misalignments. Feature similarity analysis across transformer layers provides mechanistic insight. Without GARD, degradation distortion compounds as features propagate through deeper layers, causing a progressive drop in cosine similarity to clean representations. With GARD, restored features maintain high fidelity throughout the pipeline, suppressing error accumulation before it reaches the decoder. There are practical trade-offs to acknowledge. Diffusion-based denoising requires iterative ODE solving. In the standard implementation, 50 first-order Euler steps are used to integrate the learned velocity field. This introduces latency that matters for real-time robotics, autonomous navigation, or AR applications. The authors note that future work will focus on efficient denoiser designs, distillation techniques, and multi-layer denoising strategies to reduce error accumulation and improve inference speed. GARD represents a meaningful shift in how we handle degradation in 3D vision. Instead of treating restoration and reconstruction as separate stages, or accepting the information loss of compressed latent spaces, it leverages the geometry that is already mathematically encoded in modern transformer backbones. By restoring representations where cross-view consistency is explicitly modeled, GARD simultaneously recovers accurate 3D scene geometry and high-quality imagery. For anyone building systems that operate outside controlled environments, this kind of representation-level robustness is essential. The code and benchmark details are publicly available, so I encourage you to experiment with the framework, test it against your own degradation profiles, and share how you adapt it to real-world pipelines.